Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.11, crazy optimization, multiple debates, and more coming up. So with every new kernel, we have a new message from Linus that tells us that the last week of the kernel was pretty quiet and that right now he has a lot of things to do because he's going to the Open Source Summit in Europe, he's going to the Kernel Maintainers Summit also, so there's a lot of things that he needs to do. He also has a bunch of pull requests on his desk ahead of the merge window, so yes, there's a lot that he has to do. The next week will probably be a bit slow, but for now, we have a new kernel to talk about. So without further ado, let's get into the features. Let's talk about our favorite file system, bcachefs, that has a bunch of new things into it. And let's start with the conversion to the new mounting API. Now the big reason why we're seeing more and more file systems switching to that new mounting API is because the new one has better logging. So of course everybody is going to switch to it someday, but now we have most file system that have already switched. We also see better lock depth coverage. So lock depth is a small tool that's there to detect deadlock situations. So when two locks are locking the resources of each other, so they both wait infinitely. So that tool is there to detect those situations. That's meant for devs, not really for the end user, but it still helps a lot because now the devs can actually debug what's happening and make sure that those situations don't happen. We also see self-healing on read IO checksum errors. Now, the way that it works is that if it gets a read error, it's going to try to read again a couple of times. And if it gets an error-less read, it's going to rewrite it elsewhere in order to make sure that the data isn't permanently lost. So of course, that's good news for self-healing. We also see the big rewrite of the disk accounting code. The big reason why we're rewriting this code is because the older disk accounting code wasn't scalable. So of course now it is, and we also see at the same time more counters that were added. We have counters for compression type and ratios. We see per snapshot ID usage. We see per v3 ID usage. So we see a bunch of new counters that are added, and while they were added, they also added stripe sector accounting. So that part is needed to do erasure coding. When we're talking about erasure coding in bcachefs, you should always think RAID 5 and RAID 6. So we're all waiting patiently to have our good old RAID 5 and 6. But I can tell you somebody that wasn't patient, it was Kent Overstreet, the creator, of course, of bcachefs. So there was big drama between him and Linus Torvald. Now, it's always the same thing with these two. We always see Kent violating some kind of rule in the Linux kernel, and Linus ends up sending a strong worded message saying, hey, you shouldn't do that, there are rules, follow the rules, for the love of God. And then it ends up with Kent always trying to say that his code is either superior or that his method are superior, which is completely useless because of course procedure still exists even if you're a god. So it's not really a real drama because normally you could be split in the middle and have some kind of position on one side or another, but in this case there's not really a Kent position here. He's just not following the rules, and he really should be. I can understand that it's a project that he's really carrying in his heart and he really wanted to push forward as fast as possible, so that's why he's acting in this way, and he's always acted in this way in reality. But hey, he should really follow the damn rules, but we kinda know that it's never going to happen with him. So now let's talk about other file system like XFS that now enables FitTrim for real-time devices. So we know when we're talking about something real-time in the kernel, we only mean that it has a set latency, meaning that when you reach to have the receive, to read, or to write data to a device, we are expecting it to always take the same time, the same latency. So on those devices, when you put your XFS in that mode, you normally don't really want to use trim commands, because trim is that special command where you're kind of saying to the hardware, hey, I have this chip that I'm not using currently, do whatever you want to try to heal your system, because I don't need it, right? So normally when you're doing those kind of command, it can interfere with real-time devices. So it's interesting that XFS managed to kind of fix that issue and still managed to have trim command work. Now, fit trim command are just a batched version of trim command, so multiple trim command in one. Yes, so that's great that XFS managed to fix that. But it's not only XFS that has good fix, we have a massive performance gain from, who would have thought, ext4. Yes, ext4 has a 20% performance gain on journal transaction. Wow, how did they make this? Well, turns out that there was some optimization possible and that some code in the journal code wasn't really that optimal. So now, if you're doing things like creating a lot of small file, you will see a 20% performance gain. That's insane. That's not something that we're seeing every day. It's not something that we're expecting to see every day, especially from an old file system like ext4. So now let's talk about F2FS, which has now compatibility for the getFS sysfs path command. And that command is a standardized way to get access to the sysfs path of the file system. Now, sysfs is a standardized way for the system to get some information about a lot of the subsystem working in Linux. So if you want to, for example, have some information about, hey, what's going on with my file system, how many files do I have on my file system, and all of those information, you can go reach those information through that pseudo file system called the sysfs system, where you're going to be able to get all of that information. Now, the getFS sysfs path is something that can't overstreet. Yes, the dev from bcachefs added to the kernel, and now we are using it through ext4 and bcachefs that was added on the last kernel, and now F2FS. And also, while we're at it, F2FS had a couple of small optimization that happened because of the use of the age threshold based garbage collection. So they enabled it dynamically in some cases, which enabled for some optimization. And now let's go quickly to exFAT, where we have a deadlock fix. So you remember those two locks interlocking each other? Well, there was a bug that could happen where a deadlock could happen, and now it's been fixed. So that's always a good news. We also see the introduction of support for the ID mapped mounts. So the ID map mount is there to be able to expose the same files on an hard drive to different ownership, meaning that if you have, let's say, a USB key with your home directory on it, well, you can switch between computer, and even if the two computers aren't exactly having the same ownership IDs, well, the same user IDs and the same usernames, you will still be able to use those drives because you've mapped them with ID mapped mount. So that's a big use for them. So that's why it makes a lot of sense with exFAT. So now it's integrated. And while we're talking about exFAT, let's talk a little bit about NTFS, which right now we've added the file attribute changes with the change attribute command, which is good because we can now add compressed and immutable attributes to file using that command. Now it's really fun to see that we're more and more getting more support for NTFS on Linux, because we could remember before, well, 10 years ago, when you were using NTFS, it was kind of a hit or miss. Sometime you would have a great experience and other time you would have a really bad one. Often it was, if you had the modern version of NTFS, good luck. But now it really feels like no matter what NTFS file system that I'm putting on a hard drive, if I'm using it across Linux and Windows machine, it's still working pretty great. Just like the new BTRFS improvement that we have. So we have improvement to the background block group reclaim, which is a system that goes and retake over allocated memory by BTRFS, or if memory isn't used anymore, it can also grab it. So it's good that we see those improvements. We also see the automatic dropping of queue groups, so quota groups, from deleted subvolumes. So of course, if you delete a subvolume, you're not really using the queue group that's within it. So obviously it should be deleted with the subvolume. So it's a good thing too. And we see the new rescue mode that allows you to either ignore invalid metadata checksum or ignore superblock flags. And that's really useful because sometimes when you mess around with the BTRFS file system, you can be in a situation where normally if you mount your file system, you cannot get your files back. And being able to use those mounting option allows you to, well, maybe read your data even if in the metadata space it's not going right. So that's always good news. And we also have some small memory allocation optimization and other small improvement as usual with BTRFS. So it is rare that we're talking about UBIFS, but we're talking about it today. So UBI, of course, standing for Unsorted Block Image File System. It's a file system made for flash memory. It's now a little bit more protected against power loss. They kind of sacrifice a little bit of performance at the altar of protection against power loss. So we lose a little bit less than 1% of performance to be able to be way more protected against power loss. Now that never really was in the mind of the devs when they made the file system. Pretty obviously, because if that's a file system for flash memory, we're not really supposed to lose power because remember, flash memory, it's pretty much for smartphone most of the time. Well, back in the day it was, but now of course flash memory is pretty much everywhere. So that's why it needs a little bit more protection. And while we're talking about protection, why not fix a 5-year-old bug with VFS? Yes, a 5-year-old bug. But first, let's just explain what VFS is. VFS is kind of the middle layer between the file systems and the rest of the Linux kernel. So when you create a Linux kernel driver or even any program on Linux, you don't really want to know what file system the Linux kernel is running on. You want to just write a file, right? So VFS will give those standardized commands to the rest of the system and will be able to translate them in whatever the file system driver needs it to be for it to work. So if a bug happened with VFS, it is with every file system. So we really don't want this to happen. Now the bug was a little bit of a crazy one. So it's a bug that if you had root privileges, you were able to mount a file system without the root privileges, which that file system would of course cause corruption and securities issues and crashes, but you still needed those privileges to do it. So you were kind of it's not really a security threat, it's just if you're messing around, you may find out. So yeah, that's a fun one, right? We also have atomic write for block device such as SCSI and NVMe storage, so that's good news. When we're talking about atomic write, we're talking about really writing without being cut in the middle. When we have an atomic operation, when talking in Linux and pretty much in computing in general, we're talking about an operation that cannot be stopped. As soon as it starts and as soon as you have the end signal, you know that it's been done. There's nothing that happened in the middle. You know that it's the next thing that will happen. So that's really important in some file system. And I think there's already some work with some patches to be able to implement some of that into XFS. So that's all good news. And going on about those good news, we can talk a little bit about those new Rust abstraction, which allows us to now write some Rust drivers for block device. So yes, if you want to make your own RustFS, you can now do it because you have those connection, those abstraction in the kernel. And while we're at it, let's go out of the file system world and just talk a little bit about Rust. So for a long time, if you wanted to compile the Linux kernel, you really needed to use the latest version of Rust, or at least a specific version of Rust. Now, there's been some work in the kernel, and they've managed to fix that, meaning that you will have a few versions that you're going to be able to compile Linux with, even if you don't have the latest version of Rust. So right now, the minimal version to be able to compile Linux will be 1.78.0. And I believe we're now at 1.82 or 1.84? I don't remember. Anyway, so we're further than that. So it's really good news that we see now that compatibility stretching and being a little bit more on the general side, because it's kind of crazy, right? If you want to compile Linux, you shouldn't be constrained to the latest version of Rust. You should be able to have some range there to be able to compile it. So of course they've made some code in the kernel to be able to make sure that newer version wouldn't cause a problem and older version don't cause problem either. So there's more code that has been added to the kernel to be able to fix that. Now, let's talk a little bit about Rust drama, because yes, there is a lot of Rust drama in this release. So it's been only 2 years that we've seen Rust in the kernel, so it's kind of a new thing, right? It's normal that we have some baby step to do in before we have something that works correctly. Now, the big problem is that one big Rust dev in Linux decided that he quit. It's not something that he wants to do anymore. And the reason that he cited is for non-technical issues. In other words, debates that were happening with his fellow maintainers. Now, he provided a video as an example of why he felt that the environment inside of the Linux kernel dev community was toxic and wasn't really taking Rust seriously.
We're almost out of time here, and I suspect part of the problem here is you're trying to convince everyone to switch over to the religion as promulgated by Rust. And the reality is that ain't going to happen because we have 50 plus file systems in Linux. They will not all be instantaneously converted over to Rust. Before that happens, we will continue to refactor C code because we want to make the C code better. If it breaks the Rust bindings, at least for the foreseeable future, the Rust bindings are a second-class citizen.
But we're kind of having two sides here that we need to understand. So, of course, I think I'm going to say some obvious things here, but please bear with me, because if you don't understand both sides, there's no way that we're going to be able to go forward for this. So of course, there's the Rust folks that want to apply Rust a little bit everywhere because they think that it's superior, and in some case it is, and I completely agree with them that Rust should be implemented more and more into the Linux kernel. That's pretty much obvious, and I think that most people agree with this. But we also need to understand the drawback that comes from Rust, because we have a lot of old maintainers in the Linux kernel, people that don't know Rust, and that are in a really, really weird situation when Rust make their way around their part of the kernel. Let me just give you two quick examples of those. Now, when you're a maintainer, you have some responsibility about the code that you're authorizing in your part of the kernel. So if somebody under you gives you some code, you need to look at that code and say, yep, all good. And then Linus pretty much signs it and says, yep, going in the kernel because my guy under me, I trust him. So that's good. We push it to the kernel. So of course, if you don't know Rust and you're a maintainer of some part of the kernel, well, you're not able to authorize that code. So of course, you're going to be extremely biased against that code because it's just a big hassle to manage. So that's one first part that is a big problem with Rust on Linux. And the second part is a little bit further than that. Right now, what we're seeing is a lot of Rust abstraction being added to the Linux kernel. Now, that's a good thing for Rust devs because they want to have as much connection to the kernel possible. Remember, when we're talking about Rust abstraction, we're pretty much talking about a USB port for Rust so that Rust can communicate with the rest of the kernel. So when we add those abstractions, we add features that are now accessible by Rust. But when we add those abstraction and we don't put anything on them, you can kind of see where it's really triggering for a maintainer to have that code to maintain. So if ever there's a bug or there's anything, they need to make sure that this code still works while they don't know Rust. So they need to make it still work. They don't do Rust, so they don't want to mess with it. And they're kind of in a place where they either go to a lot of hoops to try to make this work while it's not their area of expertise, or they treat Rust as second-class citizen, which of course is a problem too, because we don't want regression, we don't want part of the kernel that worked before to now not work. So we're kind of in this weird place where there's no real solution, and that's where I think a lot of people will get triggered, is that the truth is that nothing will move fast. We're going to see in the future more and more Rust being added to the kernel. But for that, we also need to see the old devs quit the kernel. We need to see the newer people bring Rust and more dev add Rust into the kernel for it to be feasible to be added to more and more places and to more core places where it can be used more and more widely. So right now, of course, Rust is limited. Of course, it's really hard to use Rust. And of course, it's really hard to have those conversations with fellow devs and fellow maintainers because they don't want to have those conversations and they don't want to add those code to the kernel. But in reality, we can guarantee that if somebody, let's say that somebody made a new implementation of BTRFS completely in Rust and it would be like 2 times faster and way more reliable, well, nobody would debate it, right? We would just find a way to fit it into the kernel. And that's just a fact. If you have some good code, it's going to end up working in the kernel. The problem that we have now is that we're trying to apply small patch in Rust. Well, that's not the place for it, right? Right now, if you want to create new subsystem, you can in Rust. If you want to create some big patch, you can in Rust, but it's a little bit more hard. You really need to wait until the old maintainer that we have now will go into some kind of retirement and we can get new maintainer that like Rust a little bit more and that are going to be able to support both language. But yes, that's going to take years and years and years, maybe 10, maybe 15, maybe 20 years. And that's just life. Some big system like the kernel will take time to change. That's not a surprise. That's something that's obvious to anybody who sees the kernel for what it is. So yes, it's sad, but you're gonna need to wait until everything is being written in Rust. If you want everything written in Rust, go do your own version of the kernel. But sadly, life doesn't work like that. You're just gonna have to stick with Linux with slow-moving Rust. So that's enough for the Rust rant. Now let's go into the improvement that we see to the kernel. We have the perf tool that was a little bit optimized by Intel. Remember, the perf tool is a tool that allows us to count the quantity of cycle that's used by the CPU. It can also give us a bunch of information about everything that's going on into the CPU so that we have as much information on did you make a good program? Did you make a bad program? Now you know because you ran it through perf. And keeping on those good improvements, we have easy Pacman kernel package. Yes, you heard me right, Pacman like Arch Linux. So it allows you to use the make Pacman package command to make a Pacman package of the kernel and simply just install it as a Pacman package. Arch Linux user rejoice, you can have your kernel 5 seconds earlier than whatever your repository give it to you. They also decided to remove the write prevention on executable. Yes, it turns out that it really doesn't achieve anything. So since our birth that we have looked at executables on Linux and also on Windows, right? That we've seen those executables when we try to write on them while they're running, nothing happened, we get a bunch of errors. Well, we we're getting those errors for nothing because it doesn't achieve anything. Nobody's really bothered by writing an executable as it's running. It turns out they decided to remove it. And that's actually a big plus for people that are trying to update running libraries. Because if you have a library, you're using it, and you're trying to replace it by a newer version, well, you're kind of screwed, right? But now you're able to do it because they removed that write prevention. We also added the sloppy logic analyzer that uses GPIO pins to detect sensors, CPU, and I2C devices. So it's pretty cool, but it's still something that is sloppy. The devs said in the notes that it's not something that is pretty professional. There's a reason why it's called sloppy. It's to be used as a last resort. So of course, be aware, it's not the perfect thing on earth, but you can at least detect some things using GPIO pins. Now let's rotate to BPF, so the Berkeley packet filter, where we have some new enhancement that includes a new iterator for working through bitmask and also a new notification mechanism that tells user space when a struct ups object has been detached. We're going to need to explain what a struct ups object is today. So those objects are kind of small program that you can shove through the kernel from user space. So now the kernel has some place where it has a BPF size hole where you can put that struct ups, and it will do something like TCP congestion program, or, well, a small program like that. So the advantage of having BPF doing those things is that you don't need to recompile a whole kernel to be able to change that code. You can just do a new line of BPF, shove it into the struct ups, and the deal is done. Now you can actually change while it's running. And now that we have a notification mechanism for it, we can actually know when something went wrong, because before we had just that new ability to put something there, but what was happening with it? Good luck, you have no clue. But now you can at least know when something is going so wrong that it has shut down. So that's really a good thing to BPF. Now let's talk again a little bit about Linus, because he doesn't only yell to his maintainers, he also creates some code. Yes, he created some code on this release where he added the new runtime constant mechanism. Now the reason why he needed to add this new runtime constant mechanism is because with ARM64, because he has a new machine with an ARM64 CPU with an 128 core, he is seeing some parts that aren't really as optimized as he would like them to be. So he saw that the pointer and the size of the directory entry cache, or also called the D entry cache, was being recalculated time and time again for no apparent reason. With that in mind, he created that runtime constant so that the calculation can only run once at boot, and that after that you just refer to that runtime constant to be able to get that value. So it makes way more sense when something is calculated thousands of times that you can just calculate it once and still get it saved in some variable somewhere. So that's always good to see those optimization, and I can bet that we're going to see this used a little bit everywhere, because there's just something with runtime constant, just the name makes you feel like you're going to hear this again with some crazy optimization, so I'm looking forward to it. So while we're talking about ARM64 and Linus, let's just switch to architecture specific changes, and let's talk about the new changes to make install on ARM64. Linus, now that he's working more and more with ARM64, he kind of sees some problem that he didn't see before. So there's a behavior on ARM64 that is considered standard for them. That is that when you do a make install command, it doesn't install compressed image of the Linux kernel. Now, under x86 or pretty much any other architecture, the make install command will install a compressed image. And the reason why it won't do it under ARM64 is because not all bootloader support compressed images. So it makes sense that you're not going to include that by default, because it could actually break your machine. It could make it not boot. So that's why by default make install will not install compressed images. But Of course, Linus on its system, that's not an issue, so he wants it to work. There's a command for this, it's called make z install, but after years and years of writing make install, he doesn't really want to add the z because he's going to make the mistake thousands of times again and again, so he wanted to fix it. Now, we talked a little bit with his ARM64 maintainer, Will Deacon, who said that changing this behavior would be dangerous if we don't add another option to it. You now have a compressed install option where when you enable it, when you do make install, by default, it will install those compressed image. So that new behavior becomes standard across ARM64 and other architectures. So that's good news. Linus won't have to remember to add a Z in front of the make install command. So let's stop talking about Linus a little bit and just focus on ARM64, which now has support for CPU hotplug on a CPI system. So of course that's mostly a VM thing. I don't think that you can just get a screwdriver and completely demolish your ARM64 CPU while it's running on any system without having some electrical issues. So yes, that's a VM thing, of course. That is going to be possible. Now let's go into x86, more precisely Intel, that finally got their shit together and fixed their subNUMA clustering and resource director technology that were fighting each other when they were both in use. So they're both kind of technology that are there to be able to make sure that a program only uses that part of the resources or that part of the CPU and memory. So it makes sense that they would be fighting each other if they're both in use, but it's still really a problem if you have them both enabled and need them both to be enabled. So it's a good news that Intel actually fixed it. And while we're talking about Intel, we've seen them enable Turbostat to be able to get the platform monitoring technology information. So Turbostat is a tool that lives within the kernel source tree that's there to report the CPU frequency and idle statistic, pretty much what's going on with the machine. And the platform monitoring technology is Intel's way to communicate some of those statistics through multiple computers or through multiple type of hardware. So that's why they added it to Turbostat, and it makes sense that we now have that capabilities. And still talking about Intel, we have performance limit reason that were added to the kernel. Now, if you wonder what a performance limit reason is, it's pretty much the reason why your CPU isn't currently burning a hole through your laptop. So it will give you the reason why your CPU isn't boosting into oblivion. So if it doesn't have enough voltage to boost, then it will give you, okay, it's a voltage reason. If it's because of temperature, it's going to give you the temperature reason. So it has a bunch of reasons for which the CPU can be limited. So it will give you the appropriate reason why the CPU is limited. And now still again with Intel, with a lot of news of course, we have the update to the EPP value of multiple CPU. If you wonder why is the EPP value so important, the EPP value stands for Energy Performance Preference Value. It's an ACPI value that allows Linux to communicate to the CPU how it should manage its power and its performance. So tweaking this value actually allows us to make CPU faster, but not only faster, but also more energy efficient, which actually makes a lot of change for the newer CPU. So they made the change for Meteor Lake, and they also made some change for Xeon Emerald Rapid CPU. They're going to make change to all the range of CPU because we saw on those Intel Xeon 32% faster for 18% less energy. That's crazy. Think about it. 32%, 1/3 more of your CPU and 1/6 less power used. That's insane. And that's just by tweaking a simple value in the ACPI. So of course that's something that we're going to see more and more, and we're going to talk about AMD a little bit later down the road. Everybody is using more and more those kind of small cheats to be able to get more performance out of their already existing CPU, because they can see that when you manage to play a little bit with the voltage, a little bit with the frequency, you can get more out of your CPU. And yeah, let's just talk about AMD right now. Why not? We see them They added core performance boost to the kernel. Core performance boost is AMD's version of turbo boost, so it's when you boost the frequency of a CPU on a per core basis above the standard CPU rate. So it allows us to get more performance out of a CPU, but of course for a cost in energy. And they also added fast CPPC. No, we're not talking about the Communist Party of China. We're talking about the fast collaborative processor performance control, which is a driver that allows those small optimization with voltage and frequency for the AMD side. So it kind of tries to play with the frequency and will use the same amount of power, but will give you more performance. So that's really great to see there. And while we were talking about the CPP, why not talk about their Chinese processor, the Long Sun 3, where I just like their name of CPU, right? So their Long Sun 3, which adds CPU frequency scaling, which is pretty much the same thing that we've seen above. So it allows you to play with the frequency of the CPU while you're in your operating system. And we also see a bunch more feature that they added to their architecture, but in all honesty, I don't really care about Chinese processors, so I'm just throwing them on screen and skipping to RISC-V, because RISC-V added some new instruction to their instruction set, so of course we added them to the Linux kernel, and we also added a bunch new feature to RISC-V. We added unpluggable memory, again mostly a VM thing, and we also added NUMA support. Now, NUMA support stands for non-uniform memory access. When we're talking about anything NUMA in the kernel, it's just the knowledge that some CPU core have faster memory than other. So of course, if your first core is closer to some part of the memory, it will be faster than the memory that it will be further away. So when you want to split your CPU, you really want to know those differences to be able to split it optimally. So to split the memory with the right CPU core to make sure everything is as fast as possible. So when we're talking about NUMA support, we're talking about support for splitting your CPU in an optimized way. Now, for that, you need a CPI, which is fairly rare with RISC-V, but still, it's something that exists, and you're going to need to have what we call a SRAT and a SLIT table. A SRAT stands for System Static Resource Affinity Table, and SLIT stands for System Locality Distance Information. They're both pretty much CPU information about how far away is the memory from a given CPU core. That's why they see that added to the kernel. Now, it's interesting, but those patches have been added by Intel Engineer, believe it or not. So yes, Intel Engineer on RISC-V, who would have known? Let's continue talking about some RISC-V added support, because we see added support for SPCR, again another ACPI feature. SPCR stands for Serial Port Console Redirection Table, which is something that you can use to be able to tell your BIOS that you want a console on a given serial port, so that you don't have to plug a screen or do any crazy thing like that. You can just tell the BIOS, hey, throw a console there, and Linux is going to be able to know to throw a console there. So that makes a lot of support easier. And they also added support for the processor properties topology table, which gives a lot of information about what the CPU is, what's the topology of the CPU, what's going on with the CPU. So again, more features to RISC-V that we actually need. We now have 128 gigs for memory allocation instead of 124 gigs when working with an SV39 kernel. So on RISC-V, you have multiple types of kernel depending on how much memory you want to use. So on smaller memory size, you can use the SV39, which contains 128 gig maximum. And on bigger size, you can go to 100 terabyte if I'm not mistaken, but you need to compile a new kernel to be able to do those things. So for the smallest size, there's three sizes, of course, but the smallest size Now we can use the full theoretical 128 gig that the CPU allows instead of the 124 gig that it was before. So it's good news that we can now use the full range of memory given by the architecture. So that's it for today's video. Yes, you're gonna have the second part probably tomorrow. So before we go, I want to thank a couple of people. I want to thank Phoronix. I want to thank LWN, so Linux Weekly News. I want to thank all the devs for making their documentation as clear as possible. Yes, because it helps understanding whatever the hell you're reading when you're studying those things. So thanks a lot to all of those people without whom it would be impossible to make those videos. So of course, if you want to see the next video, the part 2, subscribe, or if you're one day later, of course you can go check the second one, it's already on the channel. But for now, I can tell you, take care.